So I mean, it's good.
You made all of us breathe.
Well,
It's allowed.
Joshua.
Probably Bachelor of Science.
Well, apparently it's reserved for faculty.
This is an MIT.
Apparently.
No.
So you're
That's
top.
fine.
I mean, so we're up. Come on. You too, Alan. Apparently
Yeah, I
we
know,
can
but
move
I have
up.
to read
You
that.
like it there in the middle.
That's
ILC
okay.
is just, it's like Antonio, need the ILC. You never know.
Maybe.
Initiate.
Okay, should we get started? So it's my pleasure to welcome all of you to the 2026 Andrew Viterbi Distinguished Lecture. This is the flagship event in the Ming-Chi Department of Electrical and Computer Engineering, in which we feature eminent researchers in the field of communications. So let me start off by welcoming a few of our guests. Our Dean, Yanis Yortos, our colleague and Vice President for Presidential Initiatives, Sri Narayanan. Vice Dean, Garas Takatme. Timothy Pixon.
Whoa.
And Dragon another Vice Dean. And our distinguished former chair, Bob Schultz. It's great to see you. Did I get everyone? And let us welcome our speaker, Paul Siegel. So this is the series is now in its 25th year. The first lecture was 2002 and was given by Dr. Viterbi himself. And while his name has been attached with the School of Engineering for more than 20 years, some of you may not know, but his affiliation with USC goes back a long way. Before that, he received his PhD from our department some years ago, working with our late and very distinguished colleague, Sol Galong. He went on to faculty positions at UCLA and UCSD, and then founded the companies Linkabit. And if you're not familiar with that, I'm sure you all know Qualcomm. His pioneering work on decoding, which was embodied in the Viterbi algorithm, was obviously his main contribution, but he made many other technical and entrepreneurial contributions to communications over many years of his career, and just received an incredible number of awards: the Claude Shannon Award, the James Clerk Maxwell Award, the IEEE Medal of Honor, the IEEE Milestone Award, and most notably perhaps the National Medal of Science, which he received from President Bush in 2008. We're also honored that he holds the USC Presidential Chair, and he's a faculty member in our department. And he's on his way. He will be here in about 15 minutes, but he suggested that we go ahead. So today we're here to hear from another pioneer in the field of communications, Paul Siegel from UC San Diego. And let me turn things over to my colleague, Salman Avastamir, to introduce our speaker.
Right. Hi, everybody. It's a great honor, pleasure to introduce Professor Paul Siegel. Actually, I have known him since I started my PhD, and he has done amazing work. I printed out something, a lot of information there. I realize it's too small, or maybe my eye is getting weak. So I cannot read it. Yeah. But maybe I can tell you a little bit about the amazing career and life that he has had. So Professor Siegel actually obtained his bachelor's and PhD in mathematics from MIT. That by itself is very interesting, especially right now with the AI. Many people are thinking what to study, and many people are deciding maybe sciences are becoming more fundamental. And here is, what we see here, that there is a lot of profound engineering impact could be made if you learn sciences very well. After that, he did a postdoc in Quran Institute, and then went to IBM. So he didn't go to become a faculty after that. He spent at IBM Research, and for 15 years, he was working on memory systems there. So he was becoming the master inventor. That's the title that he got at IBM Research, which I think by itself says a lot about the mindset that he has on becoming, an inventor and doing a lot of inventions in the field. After that, in 95, he joined UC San Diego. He became a professor there. That's where he's leading and directing the STAR research group, doing a lot of fascinating work on coding theory for memory systems. He has received many awards for his works, for example, Best Paper Awards from Information Theory Society, receiving awards from Communication Theory Society, as well as, as we all know, being part of the National Academy of Engineering, which is a great honor, distinction for the works that he has done. So this is all the past, which is amazing. Congratulations to him for, having such an amazing career. But something that stood out to me is also the look to the future. It's kind of, this talk is highlighting a little bit maybe his perspective on where we should go next. And I think if we look at coding theory, memory, and AI, I can really see a harmonious way for them to come together in terms of the bottlenecks that we are seeing. For example, 2 weeks ago, there was this work by Google called TurboQuant. They use polar coding for memory compression in AI models. And they showed that with using compression techniques, you can get 10x speed up or 10x saving cost on, let's say, using LLM models. Why would that matter? Because 10x saving on the speed up is like 10x on the energy or much less chip that we would need. And because of actually that work, there was a huge drop in the price of chip companies that day. Because the realization was maybe the solution to AI scaling is not just more compute and more hardware. Maybe algorithmic way is another way to solve the problem. So I really look forward to this, great talk on the way that these topics could come together, lead us to the future. Please join me to welcome Professor Siegel.
Well, thank you very much for that kind introduction. It's really a pleasure to be here. I've mentioned to some people the last time I was on this campus was in 2005 for the Viterbi conference, which was held at the time, around the time that the school, I think, got his name. So it's really nice to be back. And I'm very glad that he and I are both still around. So, so what I want to do today is give you sort of a personal perspective on this harmonious interplay between coding theory, memory, and AI. And the way I want to do it is by sharing a few examples of recent research in my group in which these disciplines have come together in sort of a mutually beneficial way. So before I get into that, let me just acknowledge some of the students and colleagues whose work is represented here as well. There are 6 UCSD graduate students who are pictured in the top row, and a couple of graduate students from Texas A&M who are in the left of the second row. And I want to also acknowledge my colleagues Andrew Zhang from Texas A&M, and Ronnie Roth from Technion, and Tao Ji from San Diego State University. And to give my thanks to NSF and the sponsors of the Center for Memory and Recording Research. So the topics that I'm going to talk about today lie squarely in the intersection of these 3 areas. There are certainly lots of ways in which these pairwise intersections can lead to interesting problems, but the things that I'll talk about involve elements of all 3. And I think what I'll try to convey is how the arrival of AI has brought some interesting possibilities into research in coding theory and memory technology, and also sort of vice versa, that there are things in coding theory and memory technology that could potentially be beneficial to AI. So I'll give you snapshots of 4 different projects that fall into these categories that relate to these themes. The first has to do with how AI can be beneficial to coded memory in providing robustness. The second has to do with how coded memory can be beneficial to give robustness to AI. Then I'll talk about how a generative AI can be useful in dealing with the challenging problem of modeling memory behavior and in code optimization for memories. And then finally, I'll conclude with talking about some recent work on coding techniques for memory-based AI accelerators. So the first two topics I'm going to be somewhat brief, just to give you a sense of what the problem was and sort of what we did and what the conclusions were that we drew from the work. So the first topic is going to describe some work that's presented in this paper called PRNN, RNN-based detection for coded partial response channels. So the image at the top shows the insides of a hard disk drive. I'm sure you're all familiar with that. Things that appear in our external computer backup systems and in large numbers in cloud data centers. What you can see in the picture is there's a magnetic disk, and there's an armature that has a read head and a write head, and that sort of pivots to different concentric tracks on the disk for storing information. The figure below shows a model of a digital magnetic recording system. So this is intended to represent the entire process of recording information and then ultimately retrieving it. So let me just walk you through it a little bit to give you an idea of what we ended up wanting to do. So this encoder block takes the user data represented by the sequence U sub k and applies an encoder for a constrained code that sort of preemptively removes patterns that could lead to errors down the road. That produces this sequence A sub k, which is then put through a digital filter, which is denoted E squared PR4 channel, and that produces an output sequence B sub k. Now, what this E squared PR4 channel actually represents is the writing and reading process on the disk. So the steps involved in that are taking the sequence A sub k, having the write head convert it to a pattern of magnetization on a track on the disk. And then later, when you want to recover the information, the read head will convert those patterns of magnetization to some analog signal that is sampled and applied to another filter called the partial response equalizer. That's where the partial response name comes from. And what this partial response equalizer does is it sort of adjusts those sample values so that it makes it easier for the data to be detected down the road. But this process is very noisy, and so there's a noise sequence N sub k that's added to these B sub k's. And the noise represents noise that comes from the magnetic medium, it comes from the electronics, and it also captures the fact that this partial response equalizer doesn't always perfectly adjust the values to be what it's trying to get at. So there's sort of misequalization. The resulting noisy readback signal R sub k is then processed by the sequence detector. And the sequence detector then produces an estimate of that coded sequence A sub k, which is taken by the sliding block decoder that then produces your decoded data. Now, the sequence detector that I'm going to talk about is called noise predictive maximum likelihood, or NPML. And what it involves, as the name suggests, is it involves a noise prediction operation as well as maximum likelihood sequence detection using the Viterbi algorithm. And NPML is really the basis for virtually all of the detection methods that are used in modern disk drives. Now, there's one thing that's important to realize, and that is when the armature pivots to different places on the disk, that analog signal that's being recovered by the read head actually changes in nature. The bits are recorded at higher density. And what that requires is that you have to adjust that partial response equalizer and the sequence detector parameters in order to be able to operate effectively. So what we were interested in trying to do, this was around the time that that people were beginning to use AI in communication applications. We were wondering if we could come up with a neural network that could replace the sequence detector, just kind of as an experiment. Could it perform as well as the sequence detector? Could we train it to do that? And the second thing was, can we train it not only to operate well at one density, but could we train it to operate at multiple densities? Because this fact that I mentioned about the density changing, what actually happens in practice is that when you move to a different track, you actually have to swap in new parameters into these components of the system. So that was the goal, to replace the sequence detector, this NPML detector, with a neural network detector, as shown in the figure below. So there were a couple of kind of technical things that we were interested in doing as well. I'll just mention that, first of all, that the neural network architecture that we opted for was a multi-layer bidirectional recurrent neural network with gated recurrent units. You don't really have to worry about all of that, but we had a certain architecture that we chose to use that had been shown to be effective in certain other decoding applications. But we really were intent on trying to have this neural network behave the same way that the sequence detector works in practice, which is that it processes the data in a streaming fashion, in a continuous fashion. Most of the other applications just kind of process one block at a time. So we used a sliding window evaluation process, which I'll just mention sort of mimics the behavior of a Viterbi decoder. So it was a way of modifying the neural network to behave like a Viterbi decoder. And in order to make this work, we had to do some special things in terms of the training sequences, incorporating certain conditions that are required in this particular type of neural network, and also taking advantage of the underlying structure of that coded E squared PR4 channel. E squared PR4 stands for doubly extended partial response class 4, for what that's worth. But let me just share with you sort of the results and the conclusions we drew. So we wanted to test the network at two densities, just without worrying about the actual significance of the numbers. The densities were 2.54 and 2.88, so two different densities. And what the figure on the left shows is the performance when operating on sequences, noisy readback sequences corresponding to this density 2.54. So the red curve, which is kind of buried beneath some of the other curves, but that red curve corresponds to the performance of the neural network that was trained to operate at that specific density. And the figure shows the channel bit error rate versus the signal to noise ratio, which has to do with the level of that electronics noise. The curve, that's the blue curve with the blue triangles, that represents the performance of the optimized NPML detector. So the neural network did a good job of achieving that performance. The figure on the right shows the same result for the density 2.88. So the red curve, again, represents the neural network trained specifically for that density. And it certainly performs as well as the optimized NPML detector, which is the blue curve with the blue triangles. In fact, it performs a little better. But as I said, we were interested in whether we could train a single network to operate at two densities. And so the green curve in both of these figures represents the performance of this jointly trained neural network detector. And we can see that it manages to perform as well as the individually trained one, and as well as the channels that were the NPML detectors designed, optimized for those two densities. The thing that's interesting is that the curves, the blue curves with the circles, represent the performance of the NPML detectors that were designed for one density, but were being used at the other density. And so you can see there's a performance degradation that resulted in both cases. And so the conclusion we drew was that, number one, this neural network approach could be used at specific densities and also could provide some robustness at multiple densities. Okay, the second topic that I mentioned is sort of the flip side, using coded memory to make AI more robust. And this is reported in some papers having to do with functional error correction for robust neural networks, and also a recent conference paper on generalizing function error correction for language and vision language models. So let me give you an idea of what we were interested in doing. So the figure at the top is just a simple schematic of a neural network. There are node layers that contain the neurons and edge layers that contain the connections. And then there are sets of weights, denoted W, which basically determine how the inputs to a neuron are processed and in order to transfer them to the nodes in the next layer. And our premise was that in practice, these neural network weights have to be, these are the parameters of the neural network, they have to be stored in some kind of memory device. And we knew from experience memory devices, are not perfect. So there's some degradation that can take place. There's some device noise, if you want to call it that can corrupt the weights. And we were interested in how that would degrade the network performance. And presumably that would lead to some degradation that we then would want to try to recover from to restore the performance of the network. So somewhat in contrast to usual applications of error correction, we weren't interested in reducing the bit error rate. We were interested in really restoring the performance of the neural network. So the example I want to show you of this noise impact is the ResNet 18 network. It's a standard, widely used network that's used for image classification. And it's trained on a data set of images. It's called CIFAR 10. And what it does is it classifies the images into one of 10 categories. So they have like airplane, automobile, ship, cat, dog, horse, things like that. The network has 12 million weights, so it's it's not comparable to the humongous networks that we are seeing now, but it's not small. And the weights are stored in 32-bit floating point format. I'll talk more about that in a second, but I just want to mention that. So they're stored in binary form. And what the figure shows is basically the impact of taking the binary representation of the weights and flipping some of the bits with a certain probability. So it's trying to replicate the effect of noise on the network. And the figure on the left shows the classification accuracy of the network versus the bit error rate, the probability at which we kind of go in and randomly flip the bits in the network weights. And what you can see that it starts out, this is at 10 to the minus 9, so 1 in a billion probability of flipping. It's achieving its nominal performance, design performance, of about 95% accuracy. But as that bit error rate increases and you start flipping the bits more, you see there's quite a dramatic decrease in the network classification accuracy, especially when you get down to around 10 to the minus 6, so 1 in a million. And actually, once you get past that point, this classification accuracy is 10%, which means basically it's randomly guessing what the category is. It's totally failing. The figure on the right is the same experiment, but in which we flipped the bits only in some of the layers of the network. So we looked at 18 different layers, node layers in the network, and flipped just the bits in those individual layers. You can see that there's a similar phenomenon of kind of a dramatic drop-off at some point, but it's clear that some of the layers are much more vulnerable to these bit flips than others. So what we were interested in doing was seeing if we could find a way to use error correction codes to achieve efficient functional error correction. In other words, to restore the performance of the network, but do it in a way that didn't require a whole lot of redundancy in the coding scheme. So just to be a little more specific about what we did, the goal was not to protect all the bits, because you could always just take all of the weights and use a standard error correcting code with maybe 20% redundancy, and it would work. But that's a lot of extra bits that you're throwing into the neural network. So we were trying to do it in a little more efficient way. So we decided to try to look for the important bits in the layer weight. So we saw that some of the layers were more vulnerable than others, but the hypothesis was that there might actually be bits within the weights in those layers that are more important, that affect the performance more when they get flipped. So this picture just shows that floating point format that I talked about. And there's a sign bit at the left, and then there are these exponent bits and fraction bits. And generally speaking, except for the sign bit, the bits toward the left affect the weight magnitudes more, the size of those numerical weights. And so we figured that probably those were going to be the most likely ones that needed to be protected. But nevertheless, we decided, since we couldn't go in individually and check all of the bits, that would be just prohibitively complex, we decided to use deep reinforcement learning to search for the right bits to protect. And so we gave the deep reinforcement learning algorithm 3 different ways of identifying what these masks, we think of them as bit masks, determining which of the bits in the weights in a given layer should be protected. So the first one's called bit mask, where we didn't put any restriction. You could decide that you want to protect any one of those particular bits based on its impact on performance. The second one was called top bits, which is where we limited ourselves to only taking a set of leading bits in each weight representation. But the number that we picked can vary from layer to layer. So that gives the option of protecting more heavily the vulnerable layers. And then finally, this baseline method is one where we took a fixed number of the leading bits and applied it to all of the layers. And so we searched for the best option there and came up with some interesting bit masks for the different layers. And let me just show you the results that we had. So this shows the results we obtained once we had identified the bit masks, the templates for choosing the protected bits, where we were applying an error rate of 0.01, so 1 in 100, which is much larger, of course, than the point where that network failed, which was 1 in a million. We used a standard error-correcting code that we had found allowed us to protect the network performance if we applied it to all of the bits. And this plot shows the performance, the classification accuracy, versus the amount of redundancy. And by redundancy, I mean the percentage of extra bits that you need to use to protect the important bits compared to the total number of bits. And what you can see is that on the right is the baseline scheme, then top bits, and then the bit mask. And of course, the point we're looking for is where the performance begins to degrade from the uppermost part of the plot. And the conclusion was that bit mask provided the best performance. So it actually turned out to be useful to just protect some of the bits that you wouldn't think would be important. And that had to do actually with the nature of what the weights looked like. There were certain patterns within the trained network weights. And we found that bit mask achieves full classification accuracy by adding only 3.7% redundant bits versus the amount we would have had to add if we just protected all of bits, which was 21.8% with full protection. So that kind of led to the conclusion that there might be some potential here using this selective protection technique. Okay, let me move on to the next topic. This arose as generative AI sort of became a regular topic in the daily news. And we were wondering if we could use generative AI to advantage in helping us to do some of our memory modeling and code optimization for flash memories. So the model I'm going to talk about, my student named it FlashGen. It's a spatiotemporal generator for flash memory systems. So let me begin to motivate what we ended up doing by giving you sort of the background reasoning why we pursued this. So we were working with flash memories, trying to design signal processing and coding schemes. But actually, flash memory, the write and read behavior is pretty complicated. And so, in order to do optimization, design and optimization of coding and detection schemes, it becomes pretty challenging if you don't have a good model of that behavior. So there are many mathematical models that are proposed for different aspects of the flash memory behavior, but they're kind of limited in the scope of phenomena that they can model, and they're also limited in the accuracy to which they can model those phenomena. Ideally, you would have a measurement apparatus, an empirical, test stand, where you could make many, many measurements and collect a lot of data that you could use to characterize the system. But that requires a lot of time, and it also requires a lot of money. And the other reason is that for academic research groups, it's very hard to get access to that kind of capability. So we thought maybe if there's some way we could develop a generative AI model that we could just use to say, okay, we want to test this scheme, give us some signals that look like they came from a real flash memory device, and we can see how our schemes perform on those. So let me give you a little bit of a background on the structure of a typical flash memory. I'm not sure if you're familiar with this already, but we were using a so-called 3-level cell NAND flash memory. And it's called 3-level cells for a reason that I'll explain in a minute. So the flash memory chip consists of a whole bunch of little floating gate transistors that we just call flash cells. Those are the square boxes here. And the way they're arranged in the device, it's actually a 2-dimensional structure. So the flash cells are arranged in 2-dimensional arrays. And the rows are indexed by what are called word lines. And the columns are indexed by what are called bit lines. Now, each one of those cells can be programmed. That's the term used in the business for writing to these cells. Can be programmed to one of 8 voltages that are denoted, 0 up to 7. And each one of those cells, because there's 8 possible voltages, it stores 3 bits. So that's the triple-level cell terminology. Now, there's some unusual things about the technology. It turns out that when you want to write data to the flash memory, you have to write the entire block at once, row by row. And each block actually represents about 3 megabytes of data. If you then want to go in and change even just the contents of one cell, you have to erase the entire block, somehow save the stuff that's there, make the changes, and then rewrite the whole block. So this process, which is called program erase cycling, is actually quite damaging to the cells. And they wear out over time and the device becomes non-functional. The other thing that's peculiar about the performance of these devices is that if you write the information, but you wait a while, wait a long time, not even necessarily a long time, to read it back, that causes some degradation in the stored voltages. And so that's yet another phenomenon that you have to deal with in terms of possibly degrading the performance. So this is a picture that shows schematically what kind of readback voltages you get. When you've written some program levels and you want to go in and read it back, you don't actually just get a perfect replica of that voltage. There's a distribution represented by these distribution functions for each one of the program levels. And so there's noise in the process. And the way in which you recover the level that you wrote is there are these thresholds that are used, and the readback voltage is compared to those thresholds. And depending on where it falls between the thresholds, you make a decision on what was written. As I mentioned, this program erase cycling increases the variance, increases the spread of these distributions, which leads to errors when comparing to the thresholds. And the retention process, waiting to read it, not only increases the variance, the spread, but it actually decreases the mean of the distribution. It decreases the average value. You can think of it as shifting those distributions to the left, which, again, causes errors. So those are 2 phenomena that are important to understand well. The other one is what's called intercell interference. It's a 2-dimensional array, and it turns out that these neighboring cells affect one another. They interfere with one another. So the cell voltage is distorted by the voltages of the neighboring cells. And it turns out that the cells that are programmed to low program levels are the most vulnerable to distortion. The worst scenario is if you have a cell with a low value, represented by L, so that could be 0 or 1, surrounded by cells that have a high value, which would be like 6 or 7. So that's yet another phenomenon that is important to model. And because of the order in which the rows are programmed or written, it turns out that interference in sort of the vertical direction is a little bit worse than interference in the horizontal direction. So as an academic group, we actually were lucky in the sense that we struck a relationship with one of the major flash manufacturers. And after gaining their trust, they helped us to build a test platform where we could make very controlled measurements on flash memory chips. So they provided us with some of their state-of-the-art commercial chips, not their state-of-the-art prototype chips, I can assure you. But we had those, and they gave us sort of the secret commands, the things that you need that they would give to their development partners to be able to place the data wherever we want in the flash memory, to be able to make those hard read decisions, read back the voltages, but probably most important, to do what they call a soft read, to actually measure those raw voltages on that distribution. So we conducted a lot of experiments, program array cycling, retention, and collected a lot of data. And we used it very, helpfully, very beneficially to help us with our, signal processing and coding research. But the problem is that, as I mentioned, when you conduct these experiments on the chip, you wear out the device. And so we were rapidly running out of chips because we were sort of burning them up in the experiments. So we thought maybe we should turn to generative AI and see if we can develop a model that can learn the relationship between what's written to the memory and what's read back. And we could use that potentially to replace the experimental apparatus. So the goal was to learn this probabilistic relationship between the voltage levels, the program levels, and also take into account the temporal phenomena, the number of times that it had been programmed and erased, and also what the retention time was. So we wanted to come up with a model that we could use as a generator that would allow us to say, okay, here's an array of program levels that we want to write, and we'd like you to produce realistic looking readback signals corresponding to that. And of course, there are many metrics we could use to evaluate how effective this would be. There are some quantitative metrics just from the designing of from machine learning, designing the model, loss function, total variation distance. And then we were really interested in the performance metrics. How well did it perform? Did it give us realistic looking results when we evaluated the performance of different coding techniques and making different measurements of the signals that came out? So after exploring a number of possible options for the architecture, we settled on something that combined a variational autoencoder, a VAE, and a generative adversarial network, a GAN. And we had seen other applications where conditional VAE GANs, conditional meaning that we could provide information, like say, we would like you to generate from this array of voltages something that looks like it was measured after 10,000 or 4,000 program array cycles with a retention time of 2 days. And so this was the architecture that we opted for because it had been shown to work well with sort of multidimensional data distributions. So it incorporated 3 different neural networks, an encoder, a generator, and a discriminator. And after training it with the data that we had already collected, so we used what we had collected, we found that the model could generate data about 36 times faster than we could measure it on the test stand, which was a big help for us because sometimes these measurements would take not just days, but even weeks or months. So the question was, how well did it perform? So let me just show you a few examples of how it performed. This figure is intended to show how good a job it does in sort of predicting what the effect of the program array cycling and the retention time are on those distributions. And so it's a little bit of a busy plot, but what the plots show is for 3 different levels. So program level 2, program level 5, and program level 7. It shows the effect of program array cycling and retention on the mean of those distributions and on the standard deviation. And so let me just focus on the results for level 5. The upper graph on the left over PE cycling shows the effect of program array cycling on the mean. So we measured at 3 different program array cycle counts, 4,000, 7,000, and 10,000. And as you can see in the figure, both the measured results, which are shown in the solid line, and the generated results show that the mean doesn't change, which is kind of what we expected. And we've kind of blown up the scale here to show that they're fairly parallel to one another. And this discrepancy is actually not very large from the point of view of the applications we use. The bottom graph shows the effect of program array cycling on the standard deviation. And as I mentioned, you can see as you go from 4,000 to 7,000 to 10,000, there's an increase in the standard deviation. And the agreement between the measurement and the model is pretty good. The plots on the right are the same thing, but showing the effect of retention. So this is where we recorded at a specific program array cycle count, 7,000, and then we waited. We read back immediately, that's 0 retention time. We waited for tau time. I can't give you that number tau because the vendor doesn't like giving out those numbers, but it wasn't a huge amount of time. And then 2 tau. And you can see, again, there's good agreement in the mean behavior. And as I mentioned, you can see that the mean is dropping. It represents a shift to the left of that distribution. And the standard deviation in the lower curve is increasing. So again, you can see for all 3 levels, we were pretty satisfied that there was agreement on that score. So the next one was really this was really the test that we were most curious about, because this was to evaluate the 2-dimensional intercell interference. And that is something that's very hard to model mathematically. So we were interested to see if the model could learn, the network could learn about that behavior. So there are a total of 64 patterns of program levels that have a 0 in the middle. So there's 8 options for each of the neighbors and a 0 in the middle. And some of them are depicted here on the left, kind of color-coded, 707, 706, 607. Those turn out to be the patterns that lead to the most errors on the device. So we were interested in seeing, collecting data on the errors that occur in those middle 0 cells, and then generating model created data and looking at the errors that occur in those 0 level cells and seeing if they agree on which patterns are the worst ones, which patterns create the most problems. 707 was expected to be the worst because that's the highest level, the lowest level, and the highest level. So the pie charts on the right basically show a way of representing the results. We counted up all of those 0 errors, and we asked, okay, how many of them had a certain pattern in the horizontal direction when there was a failure, and how many had a certain pattern in the vertical direction when there was a failure. And we wanted to plot those relative frequencies. So if you start at the 3 o'clock point on the figure and go around counterclockwise, each one of those sectors corresponds to one of those patterns. And the size of the sector represents the relative frequency of that error pattern occurring. There are 23 of the error patterns that we consider dominant because they had the highest frequency of occurrence. The remaining 41s are kind of lumped together in this light green slice. So on the upper curve are the upper plots are the results for the measured data. The one on the left is for the horizontal direction. The one on the right is the vertical direction. We wanted to compare those to what we found with the model data. And so those results are shown in the pie charts down below. And generally speaking, there was pretty good agreement in terms of ranking the severity of the different patterns, which were the dominant ones, and also even their kind of absolute magnitude of their frequencies. Oh. Hello, thank you for coming. In both the word line, the horizontal and the vertical direction. So we were very pleased to see that the model seemed to be able to learn this 2-dimensional behavior. So then we ended up using the model for a number of applications to evaluate the performance of various codes, to optimize the position of the thresholds for when we're using these codes. And we also used transfer learning to kind of soup up the model so that it could handle a case where additional coding techniques called constrained coding were in use. So I won't belabor that result. I just mentioned we have some plots that show that the model, again, did a good job of replicating the measured results. So let me turn to the last topic, and that has to do with coding for memory-based AI accelerators. And this is work that really began with some papers by Ron Roth and Andrew Zhang on analog error correcting codes. And we've got some recent results that are going to be presented at the upcoming IEEE International Symposium on Information Theory and that have been submitted to the Transactions on Information Theory. But let me just give you an idea of what the problem is that we're trying to solve. So, as we know, advanced AI models like LLMs, consume an enormous amount of energy and compute time. But people have proposed, including some of your faculty members here, analog in-memory AI accelerators that can help. The problem is that when you're doing these analog calculations, they're prone to numerical errors. But as we saw with the results on the functional error correction, certain types of AI applications are not super sensitive to small errors, but they're sensitive to large errors. And so the goal was to try to come up with an analog coding scheme for use with these in-memory AI accelerators that would ignore the little errors, the tolerable errors, but still be able to distinguish when there's a big error. So this is a schematic of a crossbar architecture that includes resistive memory elements that are connected by horizontal and vertical connectors. And this device, this architecture can be used for vector matrix multiplication. So that suppose you were trying to multiply a vector U times a matrix A and get the result C, as shown down here at the bottom. What you do is you take this architecture, this array, and you program the resistive elements to have conductances that represent the entries in the matrix A. So that's what these AIJs are. Then you apply a signal to that array, here denoted U0 to UL minus 1. That represents the entries of the vector that you want to multiply by the matrix. And then sort of magically at the bottom of the vertical conductors, you get the output C. The question is, how do you protect against those errors that I was talking about? So there's something interesting that happens here. In contrast to what you do normally for data communication and data storage, here you don't encode the data, you actually encode the matrix. And so this would be particularly applicable in like an inference scenario where you've got a fixed matrix that represents the neural network weights. You're not going to be changing that. And so the idea is to add redundancy to the matrix, not to the data. And so that's depicted here. You take the matrix A, you encode it to A followed by A prime, represented in green. And basically you expand the size of your crossbar to include columns that represent this redundancy matrix, shown here in green. So how do you get those redundant entries? You do it by applying an analog error correcting code. So you apply a code that takes the values of your original matrix A and generates some redundant values that are then stored in those extra columns. So every row of this encoded crossbar now is a code word in that analog error correcting code, and the output, the expanded output C, which contains the desired result, U times A over here, plus some redundant stuff, that's also going to be an element of the code because it's just a linear combination of the rows. So in order to kind of get a handle on what you want to do more specifically, it helps to have a more rigorous model of the noise in this multiplier. So this is represented by this expression here. The output of the multiplier, which is denoted Y, is going to be a valid code word, the thing you want, plus a tolerable error vector called epsilon, plus this outlying error vector that you want to flag, you want to identify. So these tolerable errors take values that are between minus little delta and little delta. So that's supposed to be a small value. The outlying error can be larger. And we're going to be interested in the positions where the outlying error is not zero. That's where we want to, be able to identify when that happens. But we're particularly interested in where the values of those outlying errors are big. So they're larger than some capital delta, which is bigger than the small delta. So just for convenience, we use a notation for the positions where it's non-zero. We call that the kind of, ironically, the zero supports of zero of E, and the positions where they're big errors, supports of delta. So the goal is to flag those large outlying errors that exceed capital delta, and you'd like to do it for the smallest capital delta. Now, this is a rather complicated technical-looking slide about what we want the error correction code to do, but it's actually fairly easy to describe in words. So suppose you have this noisy output, this Y, and it can be represented as a code word plus a tolerable error vector plus the outlying error vector. We will say that a code C is tau error locating and tau plus sigma error detecting if you can find a decoder such that when the outlying error has fewer than tau plus sigma non-zero values, the decoder does the following. If in fact the outlying error has less than or equal to tau values, non-zero values, it gives you a set d of y that is in the support of the error vector E, but most importantly, it contains all the positions where the large errors occur. If the outlying error vector has more than tau errors, but less than or equal to tau plus sigma, then we want the detector to do the following, which is a little bit strange. We still want the output of the detector, the decoder, to tell us where the large errors are, but it will only do that if there exists another representation of this noisy vector that involves an outlying error vector that's got fewer than tau errors. If that can't be done, then it outputs a kind of an error flag, an exclamation mark saying, whoa, something's wrong. So the big question is, when is a code going to be tau error locating and tau plus sigma error detecting? Now, for those of you who have any familiarity with classical error correction coding, there's a very simple rule for deciding when a code can correct tau errors and detect tau plus sigma. That is related to the property called the minimum distance of the code, which is just the number, it's the smallest number of positions in which two valid code words can differ. And the rule is very simple for when you can have a code with this property. You just have to ensure that 2 tau plus sigma is less than the minimum distance. And that's kind of represented schematically by this graph, where the inner circle is the words that differ by less than or equal to tau positions from a code word. And then here's the larger circle, tau plus sigma. The catch is that this isn't going to be enough for the analog codes. Because remember, we're trying to deal with a situation where every single position in the code word could be distorted by one of those small tolerable errors. So just counting the number of positions that are changed is not going to be enough. So something more refined than the minimum distance is needed. And that's a concept that was introduced by Ron Roth called the M-height profile. So it's a set of numbers, h sub m, associated with the code, where m runs from 0 to 1 minus the length of the code words. And I just want to share with you the theorem that he proved that kind of has a kind of a conceptual similarity to the one I just showed for classical codes, but it's different. What he says is that let C be one of these analog codes, a real valued code, and choose your capital delta and your little delta, and choose your number of errors, tau, and the number you want to detect, tau plus sigma, not both 0. Then the code C is tau error locating and tau plus sigma error detecting if and only if this inequality holds. So the inequality involves the ratio of that large error to the tolerable error, and it involves this m height for the m value, which is 2 tau plus sigma. So that capital delta over little delta has to be greater than or equal to 2 times h sub 2 tau plus sigma of the code plus 1. So without going into too much detail, this slide does give the details, but let me just explain conceptually what this m height is. It's actually conceptually very easy to understand. You take a code word and you just order the elements in decreasing order by magnitude. So you take the largest magnitude down to the smallest. The m height associated with the code word is just the ratio of the largest magnitude to the mth next largest magnitude. And then you define the m height of the code to be the maximum of those m heights over all of the code words. So really what the m height is measuring is what's the largest ratio you can find in any code word between the largest magnitude and the smallest magnitude. And as you can see from this expression, you kind of want the m height, you want the heights to be small, because you want to ensure that this ratio, this inequality is satisfied for small ratios of capital delta over little delta. And so what does a small m height mean? It means that there's not a big difference between the largest magnitude and the smallest, which when you think about it, makes sense if you're trying to detect big changes. If you know that the valid code word doesn't have big changes in it, and you suddenly see a big change, you should be able to identify it. So this is just an example to illustrate a particular code, a repetition code, which is the simplest code where you just repeat the symbol n times. And what the theorem says is that because the m height is can be computed rather easily, in this case, to be 1 for all values of m. What it tells you should be able to correct or locate roughly half the length of the code in terms of number of errors. And you can do that for a ratio of delta to capital delta to little delta of 4. So what this plot shows is results for a particular noisy output, y, with the elements ordered in decreasing order by magnitude. And this particular y vector can be represented in 2 ways, as a code word plus a tolerable error vector plus an outlying error vector. So that's, again, different from classical scenarios. So doing error correction could be difficult. There could be 2 possible candidate code words. So it can be represented in 2 different ways. One of the code words is labeled C, the solid horizontal line. The other code word is the horizontal line labeled C prime. And there are 2 error vectors, the red E and the green E prime, have their outlying errors in the positions to the outside of these arrows. So the red E, its error positions are in position, these are labeled 0 through 11. It's a length 12 code, 0, 1, and 10, 11. Sorry, the red one is 0, 1, 2, and 11. And the green outlying error vector has errors in positions 1, 2, and 10, 11. And what the decoder does, that's designed for this code, it outputs the intersection of those 2 sets, 0, 1, 11. Now, in this particular figure, I didn't have those outlying errors be huge because it would be sort of off the chart. But it's just to illustrate the way in which this type of code can locate error positions. So the current status of this research is there are linear programming algorithms to compute the M height profile. It actually turns out to be very difficult to compute the M height profile. And these algorithms are useful, but only for short codes, like up to length 20. There are some recent results that are in our recent paper on ways to characterize the code words that achieve the maximum M height. So that can be helpful. If you can identify those, you can calculate the M height. And then there's some combinatorial characterization of the M heights in terms of maximizations over the heights of a finite set of words that you can identify. But in general, it remains a very hard problem. We also have some recent constructions involving structured analog ECC codes that are kind of geometric in nature. And for those, we can use these results to compute the height profiles. So that includes, I'll just mention some so-called spherical codes and their dual codes, and there's connections with frame theory. The other interesting question is how to integrate this with AI, since that's the objective. And there has been a demonstration from HP a while ago where they took a simple one of these analog error correcting codes and incorporated it into one of their memristor crossbar arrays and used it to improve the performance of a network that they were using, a convolutional neural network, to recognize handwritten digits. But as I say, many challenging open problems remain. I couldn't resist showing, this is a picture of one of those geometric codes. So the code words are obtained by just taking combinations of the rows of this matrix G that have 0, 1, and the golden ratio in the elements. But what's interesting is that the columns are vertices of an icosahedron, so they sit on a sphere. And you can actually determine how to produce those M-extremal code words. You just take vectors that basically lie either on the vertices, so going from the origin of the vertices, or to the barycenter of these triangular faces. And so I'll just give you the numbers here. The M heights for this code, it's a short code. It's only length 6, dimension 3. But these are actually the best known M heights for those particular parameters. Okay, yeah, thanks for your patience. I'll just mention that there was a recent double issue of the IEEE Bits magazine on information theory and data storage. And part 2 in particular addressed topics related to distributed storage, big data, and AI. And so you might find some additional information related to these connections among these areas that I've been talking about in there. And in particular, there's an article by Andrew Zhang and Eric Harach of Marvell Semiconductor called Machine Learning, Enabling and Enabled by Advances in Storage and Memory Systems. So it's very much aligned with the theme of my talk. I encourage you to look at that. And with that, I'll conclude. Again, thank you for your attention. I think there's a lot of interesting things that can emerge from this harmonious interplay among these areas. So thank you very much.
So much. Maybe we can open up for some questions.
Yeah.
So you go ahead.
I was just gonna ask about analog code. So I do coding, but I'm not a coding theorist by background.
Mhm.
So the coding I'm familiar with is all digital coding. How do you correct when it's an analog error and these large values could
Yeah.
take any continuous value?
So that's, this is kind of a new area. And so we ask ourselves that question every day. What's not clear, as I indicated, you could have multiple code words that are compatible with your noisy word. So how do you choose? The sense is that you might be able to choose something which is approximately the correct code word. But again, how do you make use of that in practice is not clear. The HP demonstration, they found a way with the particular code that they implemented to actually use the results of the decoder to improve the performance that they got. So they were doing some kind of, they were reacting in some way to the identification of the positions that are incorrect, even though it doesn't tell you the magnitudes, right? It just tells you the location. So I think there are ways that it can be done, but it's not exactly clear how to do it and how much benefit you'll get from it. Yeah, that's a good question. Yeah.
So in the first three sections, I think I can articulate this properly. When do you think we're going to evolve from the point where, even in the application of AI and ML to these more classical problems, we kind of deviate from trial and error and experimentation, right? So it appears for determining the architectures, right? It's these AI and ML boxes. There was a lot of going back and forth.
Yeah,
and so
absolutely.
When or how do you think we move away from that? So it's a little more like, well, if I want to design the maximum likelihood detector for something, I know how to do it, right?
Yeah. Yeah, I think, that's a very good question because you're absolutely right. We had to experiment with a lot of different architectures. Some of it is based on what people had already discovered. They had found that certain architectures work well with certain types of problems. But it was not at all obvious, which one was the right one to choose. And we had to do a lot of essentially trial and error. We found which ones worked best by trying a bunch of them. I suppose if you had a universal neural network that could solve every problem, and maybe we're getting towards that, maybe this Claude mythos is something like that, then maybe you could just plug and play. You just say, okay, give me that model, and here's the problem I want to do, and it's say, okay, here's your answer right now. But I don't see that happening tomorrow. It may happen next week, but not tomorrow.
Play devil's advocate. I think in some ways we should be designing AI architectures that are
specific,
actually, specialized to our communications problems rather than using what's been designed for language.
Yeah.
Right? And so when do we start being the architects of the right AI box?
Yeah, that is certainly the scenario that I would prefer because it gives us something to do. But
I think it might work better.
And I think it might work better. I'm actually in agreement with that. I'm agreeing with that viewpoint. Yeah. Yes.
So about your analog error question, I guess I have a sort of strategic question. Is just so it seems like what you're suggesting is modifying the hardware. In other words, that you have a redundant section, and then you can sort of recover whatever the original intended weights were after something. But what if I just decide instead that I want to use this algorithm somehow to train on the software side, create a set of weights that are implicitly just robust to this kind of error? Like, are these equivalent, or is the hardware?
What is it that you're training exactly? I'm not quite sure understood.
So, like, if I want to make a network more robust, for example, I might implement regularization or data augmentation or something. And maybe the results would be like, as you mentioned, that the network is more robust to the analog errors that you're talking So do you think that the hardware component is strictly necessary? Like, does it provide something that's software-based?
Yeah, that's an interesting question. I'm not exactly familiar, or I don't have a clear conception of how you would do it using the software-based approach. But I guess it's conceivable, yeah, that you could somehow design it to be, you're talking about making it robust to these errors somehow.
In the software.
In the software. Yeah, I don't know. I'd like to talk with you about exactly what you have in mind there, because I don't, it certainly is an interesting idea. I think one of the things about these accelerators is they're intended to operate extremely rapidly, like instantaneously. And so I think, it's possible that if you start invoking software-based solutions, you might suffer a little bit on that score in terms of, but again, you may have an idea of how that would not happen. But that's my initial reaction, is that it might introduce some kind of, some kind of a degradation of the performance that you're trying to achieve with the hardware. I think Joshua might have, if Joshua was here, he might, Joshua might have.
No, I couldn't hear from my group.
Okay.
Okay, we can discuss those offline. I have a few quick questions. For the first, a wonderful talk. Thank you. And for the last topic, the accelerator in memory computing, you need add a few extra column redundancy to cover those noise and outliers.
Yeah.
So usually, what is the ratio of the redundancy to the the real size?
Yeah, that really gets to the heart of some of the research that we're doing now, because we don't have a lot of really good constructions of these analog error correction codes. So we get excited when we get these structured codes based on geometry and so on, because they're interesting, from a theoretical point of view. But the real challenge is, if you want to make this efficient, you probably need to have larger code words, longer code words. And you saw the example I gave, it's of length 6, which would be a very tiny, crossbar architecture. But that's really one of the key problems, is how to find good analog error correcting codes that have large block length and have small redundancy, but have a good height profile that means that you can use it to correct errors. And that's really sort of a wide open problem right now.
Yeah. Sorry. Quickly, to the first part, you talk about using recurrent neural network for the sequence detection. That is used during you read the hard disk drive, and you want that to be in real time, I guess, right? To be fast. What hardware to implement that recurrent neural network? Maybe something like this could do that.
That
right?
could be. I mean, that was a big issue with that initial project. So, I mean, a question that we often get is people say, "Oh, that's great. You trained the neural network, and it was able to perform well at a fixed density, and it was even able to perform robustly at multiple densities. What's the complexity?" So in the paper, we do, kind of a computer science oriented complexity analysis. And you can make statements like, the complexity compared to, since we were working to compare to this NPML, which is based on the Viterbi algorithm, we're trying to compare the complexity of the number of operations. And if you assume a very, very large, very long code sequence, then you can make statements like they're both big O of the length. But, big O, there's always that, annoying constant that's in front. And the constant's pretty big for the neural network. You would need some way to implement that neural network with very efficient hardware, and maybe even find new ways of implementing some of the operations that are going on in the neural network. So that's a big question, is converting. That was fine, as a kind of theoretical, thought experiment.
With those hardware, it's possible, yeah.
So maybe some of the stuff you're doing, could really do that.
I will leave other questions later. Give the time to go.
Yes, you and Peter.
So yeah, very enjoyable talk. So I was very struck by the early part of your talk, because I work in robotics, and we've been experimenting with very small neural networks that fit just in a few kilobytes,
I see.
but run extremely fast at inference. Often sort of at 250 hertz or so, which is unheard of for big models. So it was very illuminating. So I'm going to go read about another piece of hardware now about drives. So thank you. My question is about something else. When you used reinforcement learning to find which masks were appropriate, that is, in some sense, to find the truly significant bits.
Yeah.
We have a notion of most significant bits, and if you ask anybody who does anything, they would just say, I know which bits they are. But what you found is it's not as simple as that.
At least in some cases.
At least in some cases. Related to the question I think Joshua's student asked is, are you able to exhibit networks where, in fact, random choices of bits is perfectly fine? That there is no sanctity to bits A or B. And if so, then wouldn't you just design with those networks, and then you don't need analog error correction of the type you're describing?
Yeah.
And I was just intrigued, since you probably searched the space, whether those examples are relatively scarce and kind of contrived, or whether they may secretly be the norm.
Yeah, that's a really interesting question, and I'm not sure of the answer. I mean, we were surprised to find with the ResNet network that when we couldn't figure out why the bit mask template was best. Why would you protect least significant bits in the numerical value when it's pretty clear that losing the bit in the most significant positions will dramatically change the network weight? So it turned out that in that particular case, we actually looked at the trained network weights and their representations to see if there was any pattern, that suggested why some bit in a weird position was being chosen. And we can't really explain it, but we found that there were certain positions that were predominantly zeros or predominantly ones among all the weights. And it turns out that in terms of the impact of one of those bit flips, flipping a 1 to a 0 versus flipping a 0 to 1 actually has a different effect on the magnitude. And so, what's that?
The entropy is lower.
Yeah, there's something going on like that. And so there were positions where the bit value was predominantly the one that if you flip it, it has little effect. And some of those were in the dominant, the most significant position. So we didn't really want to protect those because we didn't care if it got flipped. Even though it changed, it didn't affect the performance. But there are others positions where it was the reverse, and they were predominantly the value that if you flipped it had the biggest effect on the magnitude. And so that's what the deep reinforcement learning algorithm kind of found out. Now I have to say that we did some work with more complex models, like we did some stuff with very deep convolutional neural networks, and we did some experiments with this CLIP model, which is kind of like an LLM for assigning text phrases to images. We actually found it very hard to get the bit mask, the one that looks for arbitrary positions. We found it very hard to get the reinforcement algorithm to converge. So we in some cases, we couldn't even come to a conclusion as to what the bits were. And so we ended up just going with the top bits one, which is the one that just use the most significant bits and decide in each layer how many bits should be protected. And that, of course, was closely tied to which of the layers showed the most vulnerability to noise. Yeah, so that's a big problem, actually, is getting some of these deep reinforcement learning techniques to actually converge when you give it something which has hundreds of millions of weights to try to analyze.
Thank you.
2 points. So one on that one, recommend looking at the gradients, which is effectively, if you change a weight, which direction does the error go? And so there's a class of so-called bit flip attacks that try to identify which bits to flip to cause the largest increase in loss.
Okay.
And that may realign to your reinforcement learning.
Yeah.
We've done some work in that space.
Okay. Yeah, I'd like to.
I wanted to ask, though, a separate question. Given that you're a memory person and you looked at the error analysis of the memristors, what we've seen working with Joshua and Joshua's group is that there may be value in effectively BIST, which is apply a constant set or sequence or group of inputs and look at the outputs compared to what you expect them to be. And those constant set of inputs, in fact, you could use AI to figure out what they are. And in fact, by looking at the difference, you could actually build that into the ML model itself. So I had wondered if you thought, given you're a memory person and you've completely, I'm sure, familiar with BIST, if you hadn't thought about combinations of using redundancy and BIST to identify where the errors are.
Yeah. The answer is we haven't. What I'm wondering is, do you view the technique as helping you identify potential flaws in the network? In other words, one of the applications we thought that this might have is if, for example, to put it colloquially, if one of the memristors blew out, then you might begin to see a lot of errors in those positions. Is that what you're thinking of with using these test patterns?
That would be one. What we've actually used it is recognizing that under extreme temperature or under radiation, we see the memristor values changing resistance or effectively, and we want to create a model that not only senses the change, but adapts to the change to become robust to both temperature change as well as radiation.
Yeah. No, that's a really interesting idea. We haven't thought about that. I'd be very interested in learning.
Yeah, we could talk offline.
In that framework, yeah. Yes.
You have one more? Maybe one more, the last question.
So in your third work, you talked about using variational autoencoders and GANs for generating data samples. So as we know, like these are black box models which are not very explainable. So have you considered using causal models that are explainable and interpretable?
Yeah, I mean that really hits on an important question. So we at the time we started this work, that was when I think VAEs and GANs were sort of the popular models of the day, and there was a lot of work showing kind of what they were capable of and so on. So we sort of gravitated towards those, and we could refer to the literature that had used combinations of these for multidimensional data, because that's kind of what we viewed. We were dealing with spatiotemporal data. I mean, one of the big questions that we have now is, given some of the advances that have occurred in the intervening years, whether it might be interesting to try to do this again with a different choice of model, family of models. And I'd be very interested to see whether there are definitely some inadequacies, even though we were pleased with the way it handled the retention and the proto array cycling, and especially the two-dimensional intercell interference, and with the way in which it predicted pretty well what the performance of certain codes would be and certain detection methods. There are certainly some inadequacies. If you look closely at the pie charts, there are some still unexplained things as to why, the generated model thought some pattern would be, slightly more detrimental than some other pattern based in comparison to the experimental work. And we don't really have a good explanation for that. So it would be very interesting to see if some of the other classes of models could do a better job, and also be more robust. I should have mentioned that when we trained the model, it was based on measurements that we made using pseudo-random sequences, so that all of those patterns that I showed, the ones that they all were occurring with the same probability, the same frequency. We had hoped that you could then take a model and say, okay, I don't want to use pseudo-random program levels. I really want to focus on ones that maybe, for example, eliminate some of those bad patterns. And what we found was that the model didn't do an exceptional job of predicting the performance when you do that, when you constrain your input program level arrays compared to the measurements that we got when we did that experimentally. So that was why we used that transfer learning approach to say, okay, maybe we have to give it a little bit of a help and say, okay, now we're going to focus on patterns that have this particular structural constraint. So we're going to give you a little bit more experimental data so you can update yourself to not think that you're dealing with just pseudo-random inputs. So there are a lot of questions like that that would be really interesting to see if you could get some benefit by using other types of models.
Actually, there is some curiosity I had, maybe not technical question. Why not? You know, there is a part of your talk you talked about AI for, say, new discovery.
Yeah.
Especially, let's say, for a person who is working on theory, like yourself, I see people who are drawn to theory. They are more drawn into aha moments. Right? So for example, you see, you don't care about the problem. You care about this moment that you solve it. And there is like this joy of solving. Or maybe you discover something, a toy code, you show it to others, you talk, 30 minutes about that discovery to others. When you use AI, have you seen such aha moments? And for example, when I look at the discovery, yeah, I mean, it works, it's great. But how would you describe the aha moment? And the reason I'm asking that is kind of, if a student is interested in theory, right, by using AI, would they still experience that aha moment? Or is it going to be a new type of aha?
Yeah. So the question is whether there's a chat GPT rush is what you're really at. And I wish I could tell my students that there isn't one. That there's some benefit to thinking things through and getting the insights that come from, struggling with a problem. And that raises the issue that you and I were talking about, to what extent will these models, as they progress in capability, contribute in a significant way to scientific discovery. I mean, there's evidence that they are already. I imagine the people who developed AlphaFold or whatever it is were pretty excited.
How does it look like? You see, I have no doubt AI will lead to this. Yeah. I have a little bit, and we do a lot of AI for science. I have a little bit issue with the experiencing of that aha moment. For example, the plots you show, the green plot, that looks great. But where is the excitement? How do you describe that? I have a little bit.
The AI has the moment.
Yeah, but that's what I mean. Where is that excitement? I don't know. I don't have an answer to that.
Yeah. No, I hear you. I understand. That's what you're saying.
You need to become a robot.
Yeah, maybe there is another dimension that we should feel the excitement. All right. Thank you so much. Okay.